Alrighty then, we're going to hop into the quadrilateral exploration activity. So this is optional, but I think it's really going to deepen your understanding of where formulas come from and how all these shapes are related to each other. So we're going to start with the square, which I think is one of the most basic shapes. We learn about the square from a very young age as babies. And the square, I think we all understand already, is a shape that is flat. It has four identical edges, which are here, 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 and here. And they all meet at right angles in these corners. So each corner is a 90-degree angle. Okay, we know this already. We also know that the area of a square is simply defined as its length times its width, or its base times its height. And that is really, in this case, just going to be, let's say, side times side, right? So if A is the side, we could think of that as A times A in its simplest case, or A squared. So there's lots of different ways to think about the area of a square. Pick your poison: length times width, base times height, side times side, or just side squared. Okay, great. So we'll move that aside. We'll move that aside. Nice, good one. And then we'll move on to the rectangle. Now the rectangle really is just a more general form of a square. If we slide our square over here, we'll see that it actually has a lot in common with a rectangle. Two corners, at least so far, are 90-degree angles. And we can see that the other sides are straight and parallel. And if we kind of extend our square outwards, we can actually just produce a rectangle. So a rectangle is just a stretched out square. All four angles are 90 degrees. But now, instead of every side being the same, two are paired up. And then the other two are paired as well. Right. So that differentiates a square from rectangle, but the area is the same. The area of a rectangle should still be length times width. We didn't change really the position relationship between the sides. We just changed their sizes. So it could be length times width. It could be base times height, or it could be A times B if you want to call A the side over here, and if you want to call B the side over here. So that. Right. So this is the area of a square and a rectangle. This is already very clear to us. Now, what's really cool is that there's a lot of other quadrilaterals, namely the ones we have written on the bottom of the screen here: parallelogram, rhombus, and trapezoid, which are kind of just like special cases or special modifications we can make to squares and rectangles themselves, which is beautiful. So we're just going to keep on modifying the rectangle and the square, and we're going to see what we can come up with and see if the formulas make sense to us. So first, we're going to go towards the parallelogram. Okay, so let's take a look here. If we take our rectangle and we overlap it with the parallelogram, we could see something happens immediately. Well, first of all, if we make it look like almost a reflection, we can see that the length of the rectangle, the long side, matches up with the length of the parallelogram. They're the same. We could also see that if we put them side by side, that the heights are the same. And so the length and the height, or the base and the height of these two shapes, are identical. Interesting. Okay, but one of them's tilted, which means it does not have 90-degree angles. But there's an interesting thing we see here too, right? There's these little triangles that are forming. And this triangle here on the left side is actually not part of the parallelogram. The parallelogram is here, right? It's part of the rectangle though, right? However, if we take this triangle and we just kind of slide it over, it does become part of the parallelogram, right? So take this part of the rectangle, pop it off, and slide it over to the right side of the rectangle. And the area is, of course, still the same because this piece just got moved. So we're preserving the area, but now the entire shape of the rectangle is exactly the same shape as the parallelogram. They're exactly the same thing, which means the areas should be the same. And since we already showed that the area of the length of the rectangle is the same as the length of the parallelogram, and the height of the rectangle is the same as the height of the parallelogram, well, again, we should still have then that the area is base times height. Beautiful. So the rectangle is kind of like a template for us, but the rectangle is a little bit too big on the left side and a little bit too small on the right side. So we just move the little red triangle and we're perfectly matched up. So that means that the area of a parallelogram is the height times the base. Or again, the length times the height, or however you want to think about labeling those two things. Okay. It's important to mention, though, that we're not taking into consideration the diagonal here. We don't know what the diagonal is. If we did, then we could use the Pythagorean theorem, maybe, to do some work to find out what the height is. Because we have this little right triangle over here. And we're going to get into that in class a little bit more. But again, the area is base times height. So your goal is always to find the height of the parallelogram and the base of the parallelogram to find the area. Or if you have the area, then you can probably find one of these things as well. Okay, so the rhombus is our next shape, and we're going to understand the rhombus in terms of the rectangle once again. So if we take our rectangle, I'd like to show you something particularly interesting here. We're going to find the midpoints of the rectangle, and you'll see why in a second. The midpoints of this rectangle are going to look like this. Well, one of them is here. Another one is here, approximately here. Then there's one here, just across, and on the bottom. Ah, well, this is quite nice. Let me move this B for a second. This is quite nice because if we take a look at this special rectangle now with its midpoints identified, we can move the entire rectangle with its midpoints, and we can see how it matches up with the rhombus. Get ready. Oh, very exciting, very exciting. Oh my goodness, what do we have here? Well, it appears that the rhombus fits inside of the rectangle perfectly, and that the corners of the rhombus match up with the midpoints of the rectangle. Intriguing. So the rhombus itself is defined, we can define it as the shape that connects the midpoints of a rectangle. Okay, but what's the area of a rhombus? Well, the area of a rhombus is going to definitely be related to the area of a rectangle because it fits inside of it. It connects the midpoints. So let's see if we can be a bit clever about this. We're going to split the rectangle into 4 quadrants, 4 regions. We'll split it in half vertically, and we'll split it in half horizontally. So we can see now that the rectangle has been split into 4 blue regions like this. This top left part, the top right, the bottom right, and the bottom left. Let's observe what's happening inside one of these. Well, the rhombus itself, which is this pink fella right here, the rhombus itself, if we shade it in, covers exactly 1/2 of this blue rectangle. The inside of the rhombus is half of this blue rectangle. Okay, what if we move the blue rectangle? Okay, we'll move the blue rectangle to the right. Okay, well, if we shade in the part of the rhombus there, it's still going to be half of that blue rectangle. Maybe you see where I'm going with this. If we go to the bottom right quadrant and we color in the inside of the rhombus, that's going to fill up, once again, half of this blue rectangle. And of course, in the, in the last corner, if we fill in the rhombus, we're going to get, again, half of that blue rectangle. So now our rhombus is fully filled in. We covered the whole rectangle exactly halfway. So easy enough. The area of the rhombus then is going to be exactly half of the area of the rectangle. So it's going to be base times height over 2. Wow. Now let's understand maybe what the base and the height here mean, right? The base is this thing here, this whole width. It's the length, essentially, or right, the length. Then the height is like the width. But we can think of these in the rhombus as being the diagonals of the rhombus. So this long diagonal, and then this little short diagonal that makes a plus inside the rhombus. So not only can we say that the area is base times height over 2, but we can also say that it's little diagonal times big diagonal over 2. So you get to choose which formula you want to use, and I leave that up to you. But you're going to get those same results, right? Base times height over 2, or little diagonal times big diagonal over 2. Cool. Now we've got the trapezoid. The trapezoid now, again, we're going to think of in terms of a modification of the rectangle. Well, let's take a look. Okay, so the rectangle has a similar vibe, if I can use that word here, right? We can see that the rectangle looks like it takes up most of the trapezoid, but there's a little extra triangle hanging off. And that feels a lot like a parallelogram too, right? A parallelogram has a rectangle in it, and then it's got kind of a triangle that's moved. So we're going to take a look on the next page to see how the trapezoid formula comes to be what it is, because it's kind of the funkiest one, but there's a very nice visual way to show it. I'll come back here for a second so you can take a quick screenshot if you'd like. And screenshot in 5, 4, 3, 2, 1. All right. So for the trapezoid, we're going to see about the area of the trapezoid. We've got, it's here just two identical trapezoids. I took one on the left and I just kind of flipped it. I rotated it and I just got an identical copy on the right. Why am I doing this? Well, I'm going to show you the magic of what happens when two trapezoids come together. So the trapezoids are, well, look at that. They fit perfectly together because they are the same trapezoid. And when they're glued together, they make a very special shape. What shape is it? It's a rectangle. Whee! So this is a rectangle. Now, the height of the rectangle is just the height of the trapezoid, right? So the area of this rectangle would be base times height. But what's the base? This is the tricky part, right? We want to define the base in terms of the trapezoids. So we know, okay, fine, the heights are the same, but this base of our rectangle now is made up of two things. It's made up of this thing and this thing, which are two different measurements in our trapezoid. One of them is this big base, and the other one is the little base, right? And I'll remind you that since we flipped the right trapezoid upside down, it's just the bottom side on the right is the same as the top side on the left. So this is the little base of the trapezoid here once again. So the area of the rectangle is equal to big base plus little base, because that's the entire base of the rectangle, times height. That's the area of the rectangle. But we don't want the area of the rectangle. We want the area of the trapezoid, which is exactly half, because we took two trapezoids and glued them together. So 1/2 of this area is going to be the area of one of the trapezoids. Great. So the area of the trapezoid is equal to big base plus little base times height over 2. Hooray. The trapezoid area. Behold. Great. So the trapezoid is kind of like the love child of the rectangle and the parallelogram. And so it's really just kind of like a base times height deal, but the base is special. And we have the division by 2 based on what we've seen here in this little visual proof of sorts. So that's it. The area of a trapezoid is little base plus big base times height over 2. And then we, of course, have the double diagonals divided by 2 for the rhombus, the base times height for parallelogram, base times height for rectangle, base times height for square. Gotta love base times height, huh? So that's it for quadrilaterals. I'm not going to get into the details of what the area would be for like a random quadrilateral, but I will get you excited by telling you that if I draw a random quadrilateral with just the weirdest shapes, right? Let's say I do something like this, okay? This is definitely not a parallelogram. It's definitely not a trapezoid. It's definitely not a square. It's not a rhombus either. All the sides are different. All the angles are different. I'll give you a few seconds to think about how you might go ahead and try and think of solving or figuring out the area of this shape. Of course, I haven't given you any length measurements, but let's say I did. If this was 4 and 5 and 6 and 7, maybe you could conceivably figure out how to find information. One thing you can do, give you a quick little hint. One thing you can do with any quadrilateral is you can always cut it up into triangles. So what you might want to do is just slice across here, and you have 2 triangles. Or you might want to slice across here and get another 2 triangles. Or you might want to do a double slice. Who knows? But if you just connect the corners of a parallelogram or of a quadrilateral, you're going to get triangles. And that could then be very helpful because we already learned about trigonometry. So I'll leave that here. Could be an interesting setup for some challenging test questions. Random quadrilateral, you got to find its area by breaking it up into maybe other quadrilaterals that you know, rectangles, squares, parallelograms, trapezoids, rhombuses, and maybe triangles as well. And with these shapes, we can basically produce any polygon that we want. And so we're home free. We are math geniuses, experts, pros. And with that, that concludes the quadrilateral exploration activity. So thank you for joining me for the quadrilateral exploration activity. Have a lovely rest of your day.